What is light? It seems like an easy question to answer. After all, we are exposed to light every day, and we knew much about the properties of light. We know that it casts shadows, we know that it can reflect off objects, we even know that light refracts in different mediums, and we came up with equations that govern all of that. However, this question still stumped physicists for hundreds of years. What exactly is light? Is it made up of waves or individual particles? In the 1600s, we already had a good grasp on the properties of light. The physics superstar Isaac Newton proposed that light was made up of particles. He argued that the geometric nature of reflection and refraction of light could only be explained if light were made up of particles. He also argued that waves do not travel in straight lines, therefore it cannot explain light's straight line travel. On the other side, physicists Robert Hooke, Christian Huygens, and Augustin John Fresnel supported the wave theory, and argued that refraction could also be explained as propagation of light waves in different mediums, which the speed of light depended on. Back then, however, due to Newton's fame in his previous works, people generally supported his theory and rejected others. Then came along Thomas Young. In 1801, Thomas Young devised the double slit experiment. In this experiment, light was shined through a double slit, and the light passing through the slit is projected onto a screen. Normally, if particles, such as grains of sand, were to pass through these double slits, the particles will form two regions directly behind the slits. However, in the case of light, something strange formed on the screen. Bright and dark bands can be seen. This suggests that light was a wave, and the pattern seen on the screen was due to interference of the waves coming from the two slits. When two waves with the same frequency align in phase, it constructively interferes and produces a new wave with a higher amplitude. When two waves are out of phase, they destructively interfere and cancel out each other. This was what resulted in the bright and dark fringes. In the middle of the screen, the path length of light from both slits are exactly the same, which results in constructive interference, and a bright fringe is formed. In a spot slightly below the middle, the path length from the top slit is slightly longer than the path length from the bottom slit. In fact, the difference in path length is exactly half the wavelength of light. This results in destructive interference and leaves a dark fringe on the screen. This showed that light was indeed a wave, as a pattern cannot be reproduced with particles. In the year 1900, a physicist, Max Planck, improved on the theory of blackbody radiation. A blackbody is simply a body that absorbs all electromagnetic radiation that lands on it, and is also the best emitter of thermal radiation. The Wien's distribution law attempts to model this blackbody radiation, but it was only accurate for short wavelengths. Planck tried to improve this model by quantizing the energy possessed by the atoms. Although the beginnings of quantum theory were already conceived by Planck back then, the idea of quantizing light was only later to be discovered by Albert Einstein. The idea of light being particles was really put forward by Einstein's photoelectric effect in 1905. In the photoelectric effect, light is shined on a metal plate, and electrons are emitted from the surface. The electrons can then be collected with another metal plate due to the high potential where the photoelectric current can be measured. The photoelectric effect produced four major observations. The rate of electron emission is proportional to the intensity of light. No electron was emitted when the frequency of light falls below a minimum threshold frequency. The maximum kinetic energy of the electron only depends on the frequency of light, and the electron emission begins instantaneously when light is shined on the metal. This is where the wave theory of light starts to fall apart. The wave theory of light wrongly predicts that electrons should be emitted for all wavelengths of light, as the electron could just continuously absorb energy from the light until it can break free. It also wrongly predicts that maximum kinetic energy should also depend on light intensity. The wave theory of light also couldn't explain the absence of time lag before electrons are emitted, as the electron should only leave when it has received enough energy from the light wave. To explain these phenomena, Einstein concluded that light was made out of particles called photons, and the energy of each photon is only proportional to the frequency of light. This can explain the first observation, as higher intensity means higher rate of photon emission and thus higher rate of electron emission. When the frequency of light is lower than the threshold frequency, the photon does not contain sufficient energy to emit an electron, so nothing happens. When the photon does have sufficient energy, the electron immediately gets emitted when the photon strikes it. The relation of energy and frequency also aligns with the third observation. However, if light were to be a particle, how do you explain the observations from the Duality experiment? It sounds like light should be both a particle and a wave. And it is precisely that. In 1924, French physicist Louis de Broglie hypothesized that all particles have a wavelength proportional to their momentum. If a particle has a small enough momentum, it will start behaving like a wave. With light, due to relativistic effects, although it has no mass, it still has momentum, which is described by the equation shown. De Broglie's hypothesis was later to be confirmed by George Puget Thomson's cathode ray diffraction experiment and the Davidson-Germer experiment. These experiments showed that not only light experiences this wave-particle duality, small particles, like electrons, also exhibit this property. In the experiment, electrons were beamed at different pieces of metal, and they produced diffraction patterns on the screen. This proved de Broglie's hypothesis to be correct, and that anything is both a particle and a wave.